All right, from the last video, I introduced the chain rule, explained when you have a composition of functions, what we do is we break it down using this u substitution kind of idea. Derivative of the outer function with respect to u, derivative of the inner function with respect to x, multiply them together, that's the derivative of the composition. So we're going to look at some examples of applying this chain rule to functions that are compositions of other functions. So I have three examples here that we're going to do, and I included the graphs just for fun because you can make some pretty wonky functions out of compositions of other functions. So I thought it would be fun to see what they look like as well. We're not going to do anything with those graphs; they're just there. So this first function, y equals e to the power cosine of x. Okay, so here the cosine function is stuffed inside of the e function, the exponential function with base e. So if what we need to do first, I would say, is write the outer function and the inner function. All of these functions are in the format, we'll call it f of g of x. And so I'm going to go ahead and write down f of u and then g of x. So f being outer, b being inner. Okay, so in this case, my f of u is going to be e to the power u. You can see how if you replace the u with cosine of x, then I'll say u equals g of x, right? Then you would get, if you replace the u by cosine, you would get this, right? So there's our outer function, inner function. So now what I do is I take the derivative of each of these. Now, in an earlier video, I had introduced this idea that the derivative of e to the power x is itself. Same here, the fact that it's u instead of x doesn't matter because our derivative is with respect to u. So it's just another named variable. Same exact thing here. This derivative is itself. Okay, so then we're going to get g prime of x, a derivative with respect to x for cosine of x. And as we just recently learned, this is the negative sign of x. So now I'm going to multiply those together. And that should give me the derivative of y with respect to x overall. That would be e to the u times negative sine of x. But then, of course, I want to actually write that with x only. I don't want to have u in my answer. So I'll use this substitution here. I'm going to rearrange the order as well. I'm going to put the sine of x in front. And then times e to the power cosine of x, like that. And that right there is my derivative obtained by the chain rule. So remember, the Leibniz version of the chain rule says dy over dx is dy over du times du over dx. And you can see that's what these are right here. This is the dy over du, right? Because y equals f of u. So when we differentiate f with respect to u, that's getting that derivative there. And then this is the du over dx, because as stated above, u equals g of x, right? So the derivative of u with respect to x is g prime. So when we're multiplying those two things together, that is this, dy over du times du over dx. So just wanted to clarify that. I won't point that out every time. So now let's move on to the second function. This is an interesting function. It has a very tight like diagonal asymptote here. This function very nearly is straight here and straight here. So it's almost like a corner, except it's a nice smooth corner. This function is useful for things like smooth corner, like it'd be a useful function for modeling smooth corners of like on furniture or something like that. You know, because the alternative would be like a absolute value of x, which is a sharp corner. Sharp corners don't really happen in reality. At least you don't want them sometimes. So I think of this as like the corner of a nice rounded corner of a table or something. So let's see if we can figure out its derivative. First, I'm going to write this in a slightly different way. X squared plus 1 on the inside of a pair of parentheses, and then to the power 1/2. Now remember, I can't do this. I can't do that sort of thing instead, because that just doesn't work. That's just like a false equivalence. So instead, I need to view this as x squared plus 1 stuck inside of this 1/2 power function. Written out in terms of f of g, you could say f of u is u to the power 1/2. That's our outer function. And then u is g of x, which is the x squared plus 1 on the inside. So now we'll find dy over du, which is f prime of u, which is 1/2 u to the power negative 1/2, or alternately, it could be written out as 1/2 times the square root of u. And then we'll find du over dx, which is g prime of x, and that's 2x plus 0. So having written it out like that, now we can get our answer. The derivative of y with respect to x is this times this. But I'm going to write out the first one. Instead of having u in there, I'm going to go back and get the x squared plus 1 in there, because u equals x squared plus 1, and then times 2x. And if you want, you can rewrite that with the 2x in the numerator. Actually, the 2's cancel. We could, if we want, simplify this. I want to stress, for my class, you don't need to simplify the result of the derivative. But if you wanted to, you could write it out like x divided by the square root of x squared plus 1. That's our derivative. So for the third one here, I chose something a little bit more complicated. This has a clear outer function. Clearly, the outer function is cosine on this one. So y equals f of u, that's cosine of u. But then when we do our inner function, u equals g of x, it's a little bit more complicated. It's this entire product, right? It's x squared times sine of x. So that derivative is going to be a little bit more complicated. That's okay. We can handle complications. So here, starting with the outer derivative, f prime of u, this will be negative sine of u. We've encountered that cosine derivative before. And now g prime of x is going to be something we need to find using the product rule. So what I'm going to do is I'm going to view this as two separate pieces. We'll make them blue and orange. Blue and orange. So we're going to do derivative of blue, 2x, times the regular old sine of x function, and then plus the regular x squared function times the derivative of the orange one, which is going to be cosine of x. So we can see here I'm doing a derivative, and here I'm doing a derivative, right? But overall, this takes the form, hopefully familiar now, form of like f prime g plus f g prime, except it's not f and g because these are f and g, so never mind, we can't use f and g again, sorry. Let's just call them u prime v plus u v. Never enough letters in the alphabet. No problem. Now that we've done this, we can get our derivative here for the original function. That derivative is going to be negative sine, starting with f prime of u, negative sine of u. For u, I'm going to put the original inner function back in again, x squared sine x. And then I need to multiply by this entire derivative, 2x sine x plus x squared cosine x. And that is my derivative using the chain rule. Like I said, that one is a little bit longer, a little bit more complicated, but it's still the exact same process. Now, as you practice these sort of things more and more, you will find you don't need to show as many steps as I have shown. This is the sort of thing that once you become familiar and practiced at it, you can do it all at once. You can just look at the function, kind of do it in your head, and write down the derivative. So my goal for all of you is that you get to that point. Not saying you have to. If you don't feel like you're at that point by the end of chapter 3, that is perfectly fine. If you are, great. But my goal for all of you is to, by the end of this semester, get you to that point where these derivatives are quick and easy. So I'm just going to demonstrate to you what it can look like with just sort of a one-line derivative. Suppose you want to do the derivative of the square root of the sine of x cubed plus 2x minus 7. This is not only a composition of 2 functions, it's the composition of 3 functions. You've got I'll color code them here. Got the outer function, outermost function, I'll say. And then you have sort of a middle function, sine. And then you have your innermost function, x cubed plus 2x minus 7. So doing this can be done very quickly if you've practiced the chain rules. I'm just going to show you what this looks like. You look at the outermost function and you think, I'm going to do the derivative of that first, the square root. I know the derivative of the square root function is 1 divided by 2 times the square root function. And then I'm going to write a big square root function and I'm going to put whatever was in there before, I'm going to put in there again. Now I'm going to multiply this all by the derivative of the next function down. So I'm looking back at my derivatives. I'm going to say, okay, I got your square root. That's done. Now I'm going to do the sine function. So now I'm going to do derivative of sine, which I know to be cosine. And inside that cosine function, I'm going to stick the exact same thing that was in there before. Okay, it's going to be x cubed plus 2x minus 7. And now I can say, okay, I've done the derivative of that sine function. That part's done. All right, so now I'm going to do the derivative of the innermost function, the blue one. So it's going to be, I'm going to put a pair of parentheses, and we're going to do the derivative of this polynomial using the power rule. 3x squared plus 2 times 1 plus 0. Looks like that. And I can say, okay, now I've done the blue one. And now I could say times the derivative of what's inside that function? Oh, it's just x. So I could say what times the derivative of x. What's that? It's just 1. Derivative of x is 1. So in a way, you could think of the chain rule process as ending when you get to the derivative of x is 1, and then you stop because there are no more function compositions to do. And this whole thing is the answer. So we end up with, derivative of the outermost function, then derivative of the middle function, and then derivative of the inner function. And then this sort of times 1 at the end, which is optional. You don't really need that. So that gives you an idea of what the chain rule looks like when you extend it to like long strings of functions composed together. It's actually pretty similar to the product rule in a way, because a product rule says, if you have 5 functions multiplied together, the derivative is going to be a sum of 5 terms. There's a certain structure to it. I showed that in a previous video. With the chain rule, if you have like 5 functions composed one inside the other in a chain, then the derivative is going to have 5 factors, five things multiplied together, right? If you don't count the times 1 at the end. So yeah, that kind of gives you an idea. All right, that's it for this video.